Start recording, and I better get the projector on. There we go. Okay. And how did we feel about the videos that we watched? Okay-ish? Okay, good. Let's go to Chem 12, better than the day before. And how are we feeling about kinetic energy diagrams? Let's do a thumbs up, thumbs down, thumbs in the middle. We're still thumbs in the middle. Okay, here's the deal with kinetic energy diagrams. There's not much to them, okay? There's not a whole lot to do with them. You need to know what happens when you increase the temperature. The curve gets flatter and wider. If it gets colder, the curve gets shorter and narrower, taller, okay? It gets narrower and taller. And if you have a catalyst, the activation energy becomes smaller. It gets closer to the y-axis. And that's all you need to know about it. So if you're feeling uncertain about it, if you're feeling kind of like, there's really not much you need to do with them. If you can do the questions that are in there, you're good. Like I can't ask you much else, okay? All right, so yesterday we made it to approximately here. So this is page 64. All right. Do we remember what the activated complex is? I would like you to define activated complex for your neighbor. See if you can come up with all of those points we did yesterday.
Oh, is it on stage? No. Break it down, break it down.
So your definition should answer those three questions. When does it exist? When does it come into being? What type of thing is it? An arrangement of atoms. Or chemical species. Okay, so that's what type of thing it is. It's an actual thing. It is not a moment in time. It is not an amount of energy. What are its three characteristics? High potential energy. 2, unstable. Whoops, stable. And 3, short-lived. And when does it come into being? When does it exist? It occurs when molecules collide successfully. Okay, I'm actually going to give you 3 words right now. We have the activated complex. And the reason I'm going to give you all these 3 words in the same place at the same time is people tend to mix them up. Because we have activated complex, we have activation energy. Okay, these are different things. What is the activation energy? Describe that to your partner. Okay, it is the what kind of what? Minimum amount of energy, shocking that one, required for what? Yes, there are several choices that you could write here. Okay, your choices. There might be more than this, but let's go with these ones. A collision to be successful. Yeah. For reactant bonds to be broken. The particles to achieve the activated complex state. Or the particles, let's say the particles to form an activated complex. Okay, does anyone have any other ones? I mean, there's possibly other ones, I don't know. But those are pretty good. You can take your pick. Any of those will do. All right, and if we wanted to make a diagram of the activation energy, what would we draw? There's actually a couple things we could draw. We've drawn a couple of different types of diagrams. What type of diagrams have we drawn? We've drawn kinetic energy diagrams. And we've drawn potential energy diagrams. Yes? Okay, so let's start by drawing a kinetic energy diagram. What goes on the y-axis in a kinetic energy diagram? Number of particles. And what goes on the x-axis? Kinetic energy. And see if you can draw that shape. Okay, you try and draw the shape, and then you can check with mine. Practice drawing the shape. Even if you just do it in a corner of your book somewhere, practice drawing that shape. Don't be shy about extending the x-axis if you need to actually make that thing approach zero. I kind of mucked up on mine a little bit. Now, if we were to include an activation energy on this diagram, where would it go? What would we draw? Chat with your neighbor about that. What would we add to this to add an activation energy to this curve? Just a line. And let's just say that that value is 17 kilojoules, okay? Just for argument's sake. So that's our kinetic energy diagram. Now, if we now want to draw a potential energy diagram, what goes on the y-axis? Potential energy. Okay, and that's in kilojoules. Actually, probably kilojoules per mole. This one is kinetic energy in kilojoules per mole. And what goes along the x-axis in a potential energy diagram? That would be the reaction process or progress of reaction, anything like that. Progress of reaction, or you could say it's the reaction progress, or you could say reaction occurs. Any of those are fine. Basically, you're saying this is the change that happens as the reaction occurs, okay? And let's make this one, what the heck? Let's make it exothermic. Shall we make it exothermic? All right. So what would it look like if this were exothermic? Make a little drawing for yourself. Check with your partner once you're done. If that is our reaction profile, where would we label the activation energy? Where would we start? Where would we finish? I don't know why I made such a big, long line for that last one. You could make it a long thing, or you can make it very short. Where do we start? at the reactants, the potential energy of the reactants. And where do we finish? At the peak. Okay, the activation peak. Okay, so we're going to start at the potential energy of the reactants. We're going to draw a little dashed line there, and we're going to draw an arrow going all the way up to the peak, excuse me. And then you're going to label it EA. Is good? Okay. Shall we relate these two diagrams to one another? Wouldn't that be fun? So what if I had, this time I'm going to do an endothermic reaction, okay, just for fun. Exothermic, this is endothermic. Here's my potential energy in kilojoules per mole. And this is the progress of the reaction. And because it is endothermic, I'm going to start low and I'm going to finish higher than before. Now, if I want to compare my kinetic energy diagram with my potential energy diagram, I am going to have to turn my kinetic energy diagram on its side, because right now kinetic energy is horizontal. And wouldn't it be nice if it were vertical? Yes? And in fact, I'm going to start it right here. Oh, did I do that right? Hang on. How do I turn it sideways? No, that's wrong. It can't go like that. It has to go like this. Because what I've done is I've taken this one here and I'm going to rotate it left 90 degrees. Okay? Left. Sure, I can spell left. 90 degrees. So now what was the bottom is now the this away. Yes? So here we now have our kinetic energy. And I'm going to draw my curve. I haven't really left myself enough room, but that's okay. All right. Now, if the particles have no kinetic energy at all, can they even start going up the potential energy hill? If the particles have no kinetic energy, can they start to approach each other? No, because they're still. Okay? Which corresponds to the fact that at this energy here, they have not made it up the hill. Yes? Now, if I have a particle that has this much kinetic energy, let's just say that that is 10 kilojoules. Okay, and let's just say that this is 15 kilojoules. That means that 10 above that $25. Yes? Okay. If I have molecules, these molecules in here, that have 25 kilojoules, or sorry, that have 10 kilojoules of kinetic energy, will they have enough to get up and over the hill? Or will they only go this high and then roll back down again? They'll only get that high and they will roll back down again. How much energy would they need to overcome that activation peak? So this is 15 kilojoules, that's 25. And remember, these kinetic and potential energies don't necessarily relate numerically to one another in terms of like, if you have zero kinetic energy, you just have zero kinetic energy because you're not moving. It doesn't have to do anything with how much potential energy is contained in your bonds. If you're not moving, you have zero kinetic energy, but you can still have as much potential energy as just is in you because you are the way you are, okay? How much energy do particles need to get to the top of the activation peak, which is here? And what does that look like? That looks about like 25, 30. Is that 45? Does that look like a 45 there? About, okay, so that's 45. So, how much energy do these particles need to get from the reactants to the peak? So we start at 15 and we end up at 45. So how much did they need? 30 kilojoules. So the activation energy is equal to 30 kilojoules. And if we go across here, unfortunately, I've drawn that right in the middle of where my dashed line would go. But if I continued over with my dashed line, that would be 10, that would be 20, that would be 30 kilojoules, yes? So now I can look and I can say, what is my activation energy? My activation energy is 30 kilojoules. And any particles that have more than 30 kilojoules or greater than or equal to 30 kilojoules can make it over that peak. Does it really matter if you can make these two diagrams go together in your head? No. Okay, I'm not going to make you do that on a test. But yes. Oh, that was just a hypothetical. If the molecules had 10 kilojoules, could they make it over the hill? And the answer was, if they had 10 kilojoules, they would just roll up and then they would roll back down, okay? This is just, will these particles make it over the hill? No. And the answer is no. They would get partway up and roll back down. Thank you for asking that question. Now we have it illustrated, okay? So, like I said, I'm not going to make you, turn the diagram sideways and all that kind of thing. But if you really have an understanding of what's going on, then this diagram might make some kind of sense to you. And if it doesn't, don't panic over it. Every once in a while, just go back and look at it and see if it makes more sense to you. Some ideas come quickly, other ideas come more slowly, yes? So don't be scared if you don't get this now. Maybe you get it this year, maybe you get it next year in university, okay? I will tell you, when high school chemistry was not a problem for me, but first year university chemistry, I had no idea what was happening. It does not resemble high school chemistry at all. It is like some other beast entirely. I spent the entire time going, what happened? What? Please, help. And I had not yet learned that I needed to network with the really smart people, right? To figure out, okay, you're a really smart person. You did well in the exam. I want to be your friend. Can I bake you some cookies? Right? Don't be shy about doing it. Everybody likes cookies, right? You might even find a friend in the process, right? But don't be shy because you don't have time to waste time being like, oh, maybe I'll just hang out over here and hope you'll be my friend. No, you don't have time for that. Go make friends. Make them a pie or something, or cookies, or buy them a bubble tea or something, right? Anyway, what I'm saying, that I don't know, I sort of got off on a tangent there, but my whole point is you might not understand everything right away. I did not understand first year chemistry. Now I teach AP chemistry, which is first year university chemistry. So I have a really good handle on it now, but it did not come to me right away. I had no idea what was happening in first year. Third year professor took pity on all the biochemistry students who did not understand first year and retaught it to us in our third year, and we were all like, oh, that's what it meant? Oh, okay, so be patient with yourself. Okay, so that was our activation energy. So you can now label it on a kinetic energy diagram. You can label it on a potential energy diagram. Here's our activation energy here. Our third term, we had the activated complex, we have the activation energy. Even worse, now we have one called the energy of the activated complex. I'm going to make this endothermic again. Just makes my life easier. Again, let's say that's 45. Let's say that's 15. Let's just say that this is at, what does that look like? 30? Sure. No, 33. Sure. There we go. So what is the activation energy for this diagram? The activation energy, that's what we just did. It is equal to 30 kilojoules per mole. Now, the activated complex, that is where we find the activated complex on this diagram. Right? We have our reactants. We have our products. And up at the tippy top, we have the activated complex. What is the energy of the reactants? The potential energy of the reactants. That's 15 kilojoules, yes? What is the potential energy of the products? 33 kilojoules per mole. What is the potential energy, or just the energy of the activated complex? 45 kilojoules per mole. Do you see the difference between the energy of the activated complex, which is the actual potential energy contained within the activated complex, as opposed to the activation energy, which is the difference between the reactants and the activated complex? Okay, so this one is the difference, weird D, between the reactants and the activated complex. Whereas the energy of the activated complex is just the potential energy of the activated complex. Is good? Do we feel clarification on those terms? We're good. All right, what is delta H for this reaction? So where do we measure delta H from? Where do we start and where do we finish? Yeah, delta H is equal to the potential energy of the products minus the potential energy of the reactants, right? It's the difference, and you can do it visually or you can do it mathematically. You can do it visually by saying, I start here. This is my starting enthalpy, and I finish here. This is my finishing enthalpy, and I started at 15, I finished at 33. Therefore, delta H had to be positive, and it had to be 18. Yeah. Yes. You could label it on the other side of the graph. You could totally label delta H over here. Okay, that's your other option. Yeah. Okay, doesn't matter. But if you want to do it mathematically, you can say it is my products minus my reactants, my final state minus my initial state, you know, final minus initial. And so that's going to be 33 minus 15 is 18. Are we happy with how I've written the work for that? Yeah, I want units everywhere. Okay, so I got kilojoules per mole, kilojoules per mole, kilojoules per mole. Okay, like I said, if you are asked to find the delta H, you don't need to show that work. You can just read off the graph. And if you can do the math in your head, you can be like, it's 18 and it went up, so it is positive. Okay? All right, any other questions on any of that? The sig figs, do you need to consider sig figs? Yes, but often for these things, it'll just be whole numbers that we give you, so don't worry about it too much, okay? Graphs, it's really hard to deal with sig figs on graphs because we're reading numbers off of, right? Yeah, so don't worry too much. If I do give you actual numbers, this is the enthalpy of the reactants, this is the enthalpy of the products, and I give you a couple decimal places, then yes, you would need to go to a couple of decimal places. Okay, good question. All right. Okay, so here we go. Here's a little picture. This is page 64. We're just going to scream through this because you did watch the video on it and we did just talk about this. Here are our reactants. We have H2, H2, and O2. Yes? Eventually, they come together and they form this activated complex, which we could call H4O2 with a little star, or O2H4 with a little star. And then the activated complex breaks down into products. The new bonds form. Okay, so here we have old bonds break. And down we go, new bonds form. We could also say, at the same time as old bonds are breaking, we could also say that the reactant molecules approach each other. And over on the product side, the product molecules move apart from each other. So as the reactant molecules approach each other, what happens to the potential energy? The potential energy goes up or down? Goes up. Excellent. What happens to our kinetic energy as the reactant molecules approach each other? The kinetic energy decreases. Remember, they are repelling one another, so they slow down. Now, what happens as our product molecules move apart from one another? What happens to our potential energy? The potential energy decreases. And what happens to the kinetic energy? The kinetic energy increases. And what happens to the total energy in both these situations? Total energy stays the same. How are we feeling about that? Good-ish? Okay, cool. This one, delta H, positive or negative? Negative. Endo or exothermic? Exo. Excellent. Okay. All right, so here it just breaks it down for you some more because I've drawn all over that other diagram. This is a little bit cleaner, right? As the molecules approach each other, the kinetic energy is converted to potential energy. We form that temporary unstable species called the activated complex. The activated complex rearranges to form product molecules, and the product molecules move apart and speed up. Potential energy is converted to kinetic energy. So that's a lovely little summary without all of my drawing all over it. So here's our energy barrier that we can either overcome or not. The activation energy barrier is simply called the activation energy. We already knew that. The minimum energy with which reactant particles must collide in order for a collision to be successful, or the minimum energy reacting molecules must have in order to form the activated complex. Those are the definitions that we had at the beginning, right? Or at least very similar. And they're in a box here. Yes? Anything that's important, I usually put it in a box. All right. Now, if the colliding molecules do not have enough kinetic energy, that's where we were talking about, what if we only had 10 kilojoules, right? And we don't make it up? Well, then that is an unsuccessful collision. There is no reaction. Is good? Okay. We've already practiced this. The two most common things you'll be asked to label are the change in enthalpy and the activation energy. Okay? So you ought to be able to label both of those on a diagram, and you'll have lots of practice doing that. You might also be asked to label the energy of the activated complex. If we had to label the energy of the activated complex on this diagram, where would we put that label? I would probably personally draw a little line over here, and I would say that right there is the energy of the activated complex, because then I can read it off the y-axis. Is good? I should have put that over on the side. Yes? Yeah, if you want to actually show an activated complex, you can just put a little star there. Okay, the star would represent the activated complex. Is good? Okay, cool. So here we go. Whoa, what is that? Oh yeah, okay. Sorry. I had a little meltdown. I thought that blue arrow, the blue arrow in the middle, I thought it was the labeling the activation energy. Is that blue arrow the activation energy? No, what is that blue arrow? It is the energy of the activated complex. It is not the threshold energy. Why does it say that? That's wrong. Just scribble that out. Okay. So sorry. Whew. All right, try this one. In this diagram, we have potential, oh, blah, 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 blah. It's just an example. We've already done examples. You can look at it later if you want to. So here are the two formulas that we talked about earlier. Delta H, potential energy of products minus potential energy of reactants. Activation energy, potential energy of the activated complex minus potential energy of the reactants. Nothing new there. What if I ask you to do it for a reverse reaction? Did the videos talk about reverse reactions? Going in the opposite direction, did they? Yes? Yes. Okay, I've got people nodding. So let's talk about this because all of Unit 2 is about reactions that go both forward and backwards. So we're going to start thinking about that a little bit. So if a reaction goes in the forward direction, it is going this way. Yes? We go up here, and then we go down. That is the forward reaction. If we go backwards, the products have become the reactants. Yes? So let's say we called our reactants A. Okay, say we drew the reaction like this. My reactants would be A. For the forward reaction, my products would be B. And you'll notice I've got this new kind of arrow in there. It looks like two half arrows, one going forward, one going backward. That is what we call an equilibrium arrow. It means it does go both forward and backward. That says forward and reverse reactions occur. That's what that arrow tells us. So our products, then if we're looking at the reverse reaction, we're looking at the reaction going backwards. So instead of going from A to B, we have B turning into A. So over here, we would have B, and over here we would have A. So at some point, you should also be good at reading this backwards, yes? So it's all very well and good for us to actually reverse the entire diagram, but could you make the arrows go the other way on this? Like, let's make the blue arrows go the other way. Let's go backwards now. So B has become my reactants and A has become my products. So you can read this forwards and you can say, I change from a high potential energy to a much lower potential energy. Therefore, the forward reaction is exothermic and the delta H for the forward reaction is negative. If we read it in the reverse direction following the blue arrows, I start with the products lower, or sorry, I start with the now reactants, but we can still call them products. We will. If we write the reaction like this with B on the right, we still call them the products, even though they can now react. It's confusing, but don't worry, you'll get it. We'll spend so much time doing reverse reactions, you'll all be good. Okay, so now we have our products and we're going backwards towards the reactants. We start low and we finish higher up. So delta H for the reverse reaction would be going upward. The activation energy for the forward reaction, you start with the reactants and you finish at the peak. So here is our activation energy of the forward reaction. For the reverse reaction, we start at the products and we would go all the way to the top. So the activation energy for the reverse reaction is much greater. And you can actually see it's drawn over on the right-hand side. That is the activation energy for the reverse reaction. Okay? But we never actually, other than right now, we're not going to draw the graph like this and then like this. Okay? We'll just read it forward and then we'll read it backward. If the forward reaction is exothermic, what does that tell you about the reverse reaction? It has to be endothermic and vice versa. And delta H will have the same value because the difference is the same, but the sign will be reversed. I miss having the overhead projector for this because what I used to do is I would draw it and then I would pick up the transparency and I would simply flip it over like that. It was very satisfying. This time I had to just draw two of them. That's okay though. Okay. So here we've drawn them all on, this is like without doing the reversing. Here we have the activation energy for the forward reaction in pink, activation energy for the reverse reaction in blue. Here is our delta H. Let's label our delta H forward. And our delta H reversed. Is good? Okay. Could you please do these questions and then check with your partner, and then we're going to take a 5-minute break until 25 past. So the faster you can do it, faster you get on your break. You have a 5-minute break. You do not need to write the equation. You can just read it off the graph. Okay? No need to write the equation. You need to write positive and negative. Okay? And if you want to check your answers, here they are. They're actually on the next page. If you want to check, it should be 80, 50, 100, 100, 30, negative 30. All with kilojoules per mole. Should we do stretches today? Okay, let's do stretches today. And if you're confused about any of that and you're like, how did you get those numbers? Don't worry, we can address it after we have stretched, okay? All right, everybody, up. Stretch your arms out and back. Oh, you know what we could do? We could just do like this. We could go up and then down and keep them as far back as you can the whole way through, and you can cross them over at the top. And you can cross the opposite way each time, one arm in front and then the other arm in front. All right, we're gonna do this one. Stretch those shoulders up. You can give your back a little twist while you're at it. Give your back a little twist. All right, this one's always good too. Oh, and you can do it, if you want to, you can get your side involved as well. Stretch out your side a little bit. They should have mandatory stretching classes for everybody all the time. Oh, so good. All right, do you guys want to do the figure 4? So you put your foot on your knee and then you basically sit down and you keep your chest forward. Okay, you can hold on to your desk. You can sit down and do it if you want to, but you can also do it standing. I'll go up here so you can see what I'm actually doing. Okay, so you put your foot like that, and then you sit like, oh my God, it feels so good. You need to try it. Why are you not trying it? I'm up on a frickin' desk doing this. You can try it on the frickin' floor. Come on, let's go. It feels so good. Try it. Are you kidding me? Are you too scared? You're gonna fall over. Hold on to the desk. You don't have to stand on a desk and do it. So good. Okay. Never mind, but it is one of the best stretches you can actually do for your hips. It's so good. All right. Now, I would like you to tell me, I would like you to tell your partner, how does a catalyst speed up a reaction? What does it change? Yeah? No, I heard something over here. It changes the activation energy. It changes the size of the activation peak. So you remember things in boxes are important and things in bold are important. So what are we adding to that explanation here? I want you to read it and say, what are we adding to that explanation in the first sentence? So take a look at that first sentence. This is just on your next page. So if you want to flip the page, you can do that. Okay, we are now on page 70, at the bottom of the page. Read the first sentence and tell your partner, what have we added that's important? So they lower the activation energy. How do they do that? They provide an alternate reaction path. Okay, so if you're explaining how a catalyst works, you need to have 1 and 2 in the explanation. Now, if you're asked to explain it in terms of collision theory, you would add the second sentence. So here's our diagram. What's the only thing about it that has changed with a catalyst? The catalyst changes only the activation energy. Does it change the potential energy of the reactants? No. Potential energy of the reactants is unchanged. That's because the potential energy of the reactants depends upon their nature. Have we changed the nature of the reactants? No. Similarly, what else doesn't change? Sorry? The kinetic energy? Is there kinetic energy on this diagram? So that you're correct that the kinetic energy doesn't change, but it's not on this diagram. Pardon me? Total number of particles? Yeah, that also doesn't change. But what else doesn't change on this diagram? The potential energy of the products, okay? So the potential energy of the products is also stays the same. Now, you are absolutely correct, though, that the kinetic energy also does not change and the number of particles does not change. So when I put those little dit underneath, it just means I don't want to write the same thing again. It means catalyst does not change the number of particles. It just means I don't have to write the same sentence stem again, okay? Okay, this just says that the potential energy of the reactants and the products remains unchanged. So when drawing a potential energy diagram for a catalyzed reaction, you want to make sure that the activation peak is lower for the catalyzed reaction, but you will leave the potential energy of the reactants and products unchanged. I think we've already talked about this. If we consider the nature of the reactants and we're comparing different reactants, one might have a different energy than another. I don't even know what I was going about here. I don't know. Something, whatever. Let's just go here and let's look at, ooh, here's two different reactions. Why are they different? Because the reactants are different, right? Why do they have different reactant profiles? Because the reactants are different. Look, different reactants have different energy diagrams. Whoa, that is the nature of the reactants. Yes? Not much to see here, folks. Yes? So, nature of reactants does not really affect the diagram other than the fact that it is what it is. Yes? Okay, good. How do other factors affect the diagram? Concentration has no effect on the diagram. Pressure and volume has no effect on the diagram. Temperature has no effect on the potential energy diagram. And surface area has no effect on the potential energy diagram. So you can change whatever you want about the concentration, pressure, temperature, surface area. They do not change the potential energy diagram because the potential energy just depends on the nature of the molecules. It doesn't matter if you have more of those molecules, their average potential energy stays the same. It doesn't matter if you've squished the molecules into a smaller volume, the average energy contained per molecule is the same. It doesn't matter if you make them go faster, their potential energy contained in their bonds remains the same. Sometimes people don't like that one because they're like, oh, if I make the temperature higher, I've made the kinetic energy higher, doesn't the potential energy need to get lower? The problem with that argument is when I heat something, when I increase its temperature, I am bringing in heat from outside the system, right? So I'm not actually increasing the potential energy or the kinetic energy by decreasing potential. I'm increasing potential by bringing in kinetic energy from somewhere else. Remember, energy can be transformed, but it can also be transferred from one place to another. So temperature, we would be transferring kinetic energy from the surroundings to the system, and vice versa. So one thing to note, why do any of these things not affect it? Really, it's because it's always kilojoules per mole. So we always have that ratio there. You could think of it as kilojoules per molecule as well. Okay, so it always remains the same. If I have 300 kilojoules per 10 moles, that's 30 kilojoules per 1 mole. That's 15 kilojoules per 0.5 moles, but it all works out to 30 kilojoules per mole. So that's why concentration doesn't affect it. I don't know. There's a lot of blah, blah, blah in here. Oh, look, here we go. Here I've got 2 moles of H2, 2 H2s, and an O2, right? Down here I have 4 H2s and an O2, but what do you notice about their potential energy? It's the same because they're the same chemicals, okay? Same thing with the products. Why doesn't pressure, volume affect potential energy? It's the same as for concentration. You have the same chemicals. If you have the same chemicals, they have the same potential energy. Surface area, same chemicals, just broken up into smaller bits. Temperature, I don't know why, I liked this analogy. A hamburger contains a certain amount of potential energy, yes? And it contains that energy if it's sitting nicely on the desk. It contains 650 calories. Does the calories contain the potential energy in that hamburger? Does it change if I throw the hamburger across the room? No, only the kinetic energy changes, and that changes because I'm transferring energy from my arm to the hamburger, okay? It's not like that energy came out of nowhere, it came from my arm, okay? I just like that anyway. Got excited about that. Ooh, an inhibitor, but we don't have time for inhibitors. So if there's anything about inhibitors in the worksheet, you're going to do all of 1.3e. 1.3e, do all. Okay, so that is pages 76 to 79. And next day we start reaction mechanisms. Yes. I know. If there was, it would, I would really love to do a quiz on Friday, but that's just not going to happen because there is no Friday. I would like to, let's just say that the quiz for 3, 4, and 5 is on Thursday. And then if I change my mind, it'll only move to Monday. How's that sound? Okay, Tuesday. Okay, yes? Okay. Quiz on 1.3, 1.4, 1.5. That's going to be on Thursday, this Thursday, but I reserve the right to change my mind and change it to Tuesday. Will probably be Tuesday. Okay.
Thanks for moving.
It's probably going to be Tuesday. No. Yes. Right. Well, we still have our test on Friday, wouldn't we? The unit 1 test next Friday. But it's a bit shorter. Maybe, but that means we have less time to study equilibrium. And it's harder than reaction. Yeah?
You still make the test on a Thursday.
No, it's not going to be on Thursday. It's probably going to be the Friday. I'll probably just make it a little shorter than usual.
Yeah, it'll be destroyed in calculus.
Yeah, no worries.
Thank you.
Yeah.
And the homework is going to be on.
The homework will be on Teams, yes?
Thank you.
Yeah.